I'm Tyler Sentz, and I'll be discussing the AP Chemistry FRQ number 5 from 2019 FRQs. The overall topic is the photoelectron spectrum, which is a graph that can help you find the electron configurations for an unidentified element. This question asks to find the electron configuration based on the graph, identify the element, and then solve for wavelength. A real-life example is if you want to find the wavelength of a certain wave and a technology. You can use the constants in equations and the energy, if you have it, to solve for that wavelength. The significance of this FRQ is to understand the atomic structure of an atom and electron configurations to better your understanding of AP chemistry elements.
Okay, let's begin. The complete photoelectron spectrum of an element is in its ground state is represented below. Based on the spectrum, write the ground state electron configuration of the element. So first, we're going to see that these are different energy levels, and these are represented by coefficients, so 1, 2, 3, and 4. When a peak is by itself, it's just going to be the S block. When there's two peaks, the one on the left is going to be the S block. The one on the right is going to be the P block. Same coefficients, so same thing, 3S, 3P, and then by itself, so just 4S. The number of electrons is shown by the y-axis, and so that's going to be the 2, 4 electrons, 6 electrons. So if the peak goes up to 2, that means that it's going to be 2 electrons. So this one goes up to 2, so it's 2 electrons. This one goes up to 2, 2 electrons. This one goes up to 6, 6 electrons. This one goes up to 2, so it's 2 electrons. And this is going to be up to 6, 6 electrons. This one goes up to 2, so it's 2 electrons. So this is like inside the sub energy level. That's how many electrons are in that orbital. So we're going to rewrite that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And to identify the element, we're going to use a periodic table using the configuration. Since they are an S and P block, that means that the rule is that the rho is equal to the coefficient in front. It's just equal to each other. So that means that if this is the S block with helium and this is the P block, we can write that. And also the electrons of the exponent is equal to how many blocks you count. So this is the S block. So 1, rho 1, S block, helium's S block, 2, 1, 2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. So this is going to be calcium. That's our element because it's the last one that we circled. Now, the last part is to calculate the wavelength in meters of electromagnetic radiation needed to remove an electron from the valence shell of an atom of the element. And to remove an electron from the valence shell, it would be the last energy level's energy. So E is equal to 0.980 times 10 to the power of negative 18th. And we also have a reference sheet with a different E equals HV, C equals wavelength V. Planck's constant is H equal to, speed of constant T equal to, and let's write those on our paper so that we have them. So E is equal to HV, C is equal to wavelength V, Planck's constant, H is equal to 6.626 times 10 to the power of negative 34 joules seconds. Speed of light is C equals to 2.998 times 10 to the power of 8 meters second to the power of negative 1. And we need to rewrite these equations because we don't have V or wavelength so that we can have one variable we're solving for. So we have for this one, V is equal to E over H. And for this one, we have wavelength is equal to C over V. So that means that wavelength is equal to HC over E. So then we can plug those in and we can get 6.626 times 10 to the power of negative 34 times 2.998 times 10 to the power of 8. And then over energy, which is from above, is 0.980 times 10 to the power of negative 18th. And we get wavelength is equal to 2.03 times 10 to the power of negative 7 meters.
The topic of the photoelectron spectrum was used many times in this FRQ. For the first part, the spectrum was used to solve for the electron configuration to identify what the element was in the graph. For the second part, the x-axis energy from the spectrum was used to solve for wavelength. This goes back to our real-life example. If you had worked with technologies and you defined the specific wavelength of a wave inside the technology, you could use the energy from a photoelectron spectrum of an element to then solve for what that wavelength is. This shows how important photoelectron spectrum is to chemistry and to real life because it's really important to specific energies and wavelengths and also to identify specific substances.